time for discussions. We have selected several topics. This is open discussion, so anyone can participate in that, including people who are on YouTube. They can type their questions in there, and we will repeat their questions here. The first topic is about what should the next generation of vision sensors for robotics should look like. There are two shoulds there. Do we need more computation on the vision chip? So this is the first topic, and I encourage you to participate in this. Any icebreakers?
I guess first thing which we should say is probably for robotics, one of the most successful vision chip so far has been the event-based camera, right? And that compared to other vision processors such as scan or more complex devices has much less computational or reprogrammable ability. And I guess it would be interesting to think whether events are enough. As we've already seen by some of the presentation, they can give us a super stunning result, or whether we can push it much more by moving more processing to the device.
That's a good point, because yeah, I think there are maybe other factors into that, and that's kind of like the availability of the sensors as well. I think that's kind of like if you want to do research on these like event cameras, there's a lot of support to start this. So that's I think maybe kind of like also a deciding factor in here as well. I'm not sure what others think of this.
Well, it seems to me there are two reasons why you might want to do more computation on the vision on the sensor device. One of them is perhaps because it will enable you to reduce the data volume moving downstream. The other is potentially that you have access to information that is hard to capture otherwise. So, for example, the work we've seen on high dynamic range to some extent does that.
Right. In other words, most of the works, most of the sensors, they show things that they show very cool demos that it's usually impossible to do with conventional sensors. So maybe that's the final answer. Basically, we should be able to do things that are not possible to do.
I guess there's also an issue of what does it mean to have a computation on a vision chip, right? So whether we are computing in pixels, whether we're computing next to pixels, whether we are computing on the chip but somewhere outside of the array, and what is the kind of how does the whole kind of pipeline look like? So I think that's an important question here, which I'd like to know answer to, but work needs to be done to find the answer to that question.
Yeah, I mean, I think what drove me into being interested in these things is mainly about efficiency, and I guess mainly that comes down to power and this argument that if you can do more on the sensor chip and therefore send less data to a main processor, I guess either do everything on a chip that's right there next to the processor, or yeah, do a lot of processing and then only send something abstract to your main processor. Yeah, we just need, massive, for some of these applications that we are interested in the long term for embedded vision. I just think we need orders of magnitude of improvement in efficiency, power usage, such as the sort of things that Facebook were talking about, always on vision, you know, they're talking at the moment about switching it on and off and so on, but of course you'd really want it on all the time. How are we going to get down by that, you know, thousands of or whatever it is factor of efficiency that we're really going to need? So that's the main driver for me. And it was interesting what he Yusin said in the talk about some of these decisions were maybe not so obvious. I hadn't quite thought about that. I'd always assumed that pushing more to the sensor chip, if you could, would always be, or almost always be, the right thing to do. But some of the things he said about, yeah, if the process node technology wasn't quite as advanced, for instance, and therefore it might actually be less efficient to do some things on the sensor chip than moving that data to another processor that might be able to be more efficient because, for instance, it didn't have to be so compact. That was quite interesting.
I mean, it kind of almost depends on what we mean by chip. I mean, it's always better to do things on chip than somewhere else. But you know, whether I mean, what about a stack, for example, where you have different technologies that are kind of vertically integrated? Is it still a chip? I mean, to me, it's still a chip, but you can think about it as 2 or 3 different chips. But clearly, then you can optimize different technologies for different types of computation. So we've done some designs where we had a sensor tier, which was image sensing technology. Then we had a second tier, which was an analog processor, and a third one, which is a digital processor. Actually, ours was kind of uniform stack, but you can imagine a heterogeneous system where you have an optimized image sensor technology for the sensors, an optimized technology for analog compute if you want to do some analog preprocessing, and yet another tier of digital compute for digital logic, and perhaps another one for DRAM or flash or whatever else. So keeping things compact will be always advantageous, but how the system should look like, I think that's another question.
I think going back to the always on idea, I think there's the more computation we can push onto the chip, I think we could probably say the more secure we can make it. As in, that is to say that if you have dedicated hardware for doing this sort of small first steps and encoding more interesting features, then it can make it harder for malware or something in the application layer to put out information that we don't actually want them to see. So we can pick better, you know, these are the number of faces in the image and not these are particular identities.
Right, yeah. Paul, you're mute. Yeah, if you...
I think you have to be really careful with that reasoning for 2 reasons. One, because, so for example, we've experimented with only sending edges off device. Can you really promise me that you can't reconstruct privacy breaking information from just the edge stream? I think you probably can.
As we've seen with the histogram of gradient stuff, there's a lot of reconstruction you can do.
Absolutely.
So I think the question is, if we're going to put more computation onto the vision chip, can we get all the way to something where we aren't just sending edges, we're sending feature vectors that can be trusted, as it were, because we've stripped out all the unnecessary information.
So the other pathway for vulnerability is that if this device is programmable, I just have to hack its code.
Yeah, but I mean, that's always true. Access to the hardware is access to the hardware.
Right, yeah. I think just in the interest of time, we can move to the second topic, which is, I think for me as a roboticist is kind of like important. And that is, what are the technological challenges in bringing novel sensors to robotics? Yushin mentioned a few challenges, including heat dissipation, the weight of the sensors, and all those sort of things for smart eyeglasses. But in robotics, we face similar challenges. So I'm not sure what's your opinion about this? And it obviously depends on the application domain, right? So for example, for drones and things like that, it has to be very lightweight, just like eyeglasses, smart eyeglasses that Yasin was talking about.
Yeah, isn't one general challenge just the whole system stack complexity, right? So, I mean, whenever I talk to people who develop algorithms, they don't want to hear about my stuff. They want something very general. They don't want to be restricted by the way I produce data or how I represent it. They want to program everything, and they're going to change their mind every week, right? So if you give them something customized and optimal, which is a novel, that this is where most of the novelty goes. We squeeze performance out of customization these days. I think that's, in my mind, one of the biggest challenges, how to get that accepted by the higher levels of abstraction and the people running these layers of abstraction.
I think that's an important point, right? So I think you can almost always build a circuit that is better than a general purpose circuit that, more efficient. But that doesn't necessarily mean that it will be better in the sense of being used by more people, right? So I think that is. I mean, even with the work that we've been doing on scam sensor, I mean, I was always out for 20 years. I was saying these are programmable chips, but really no one could program them. It's only when we started to develop this very, very detailed sort of programming environments where you could actually program them in C and you could sort of compile your programs and so on. It's only then that we started to see people, doing things with the system that we I thought was impossible. So there are kind of new applications coming up, and I think that kind of issue of providing the software frameworks so that people can use systems is important. And I think the more customized the hardware is, the harder it gets. And definitely this issue of, we can spend 3 years thinking about circuits, how you develop some optimized neural network architecture, only for people to decide that, the nonlinearity that you're using is not fashionable anymore and no one wants to use it. So, yeah.
Speaking of the customization sort of route, I wonder how sci-fi an idea it is to sort of get to a point where customizing a chip is like how now people have 3D printers at home. I mean, 10, 20 years ago, people didn't think that they could make their own products and their own 3D objects at home. And now you sort of can. I wonder how long it'll be until every research lab can do a bit of chip fabrication in the corner of the office and make what customized or, partially customizable chips they need.
I think it's certainly hard with the state-of-the-art silicon technology. It's just too expensive. You cannot afford this. But there are other interesting technologies on the horizon. We've been working with plastic electronics, printed electronics, where you can, at a very low cost, customize your circuit and have a very quick turnaround and get them fabricated and tested in a matter of weeks. So and these are not, this is not 7 nanometer CMOS or 5 nanometer CMOS. But you can end up with your, customizable circuits in that way. And things like programmable logic devices and so on, again, these are the ways in which you can end up with a custom silicon. And there is some sort of pathway, semi-automated pathway from your application to what we call silicon. Yeah.
Thank you, Boris. So some of you will have heard me already say that the fundamental business of computer architecture is reducing the interpretive overhead, is having your cake and eating it, having programmability without having to pay the price much.
Mm-hmm. Mm-hmm. Yeah, exactly. So actually, I think that brings us to the next topic, which is basically what exactly we're looking from these on or near sensor processing system. Is it just low power, high performance, or are there any other things that we're not considering yet and might be an issue in the future?
I guess something interesting to think about might be how we can feedback from the algorithm side. back to the sensor to try and do more adaptive sensing. Just like how like AI work, we might be able to move the sensor in the direction we want to, and that should feed back off the algorithm side. And maybe if we can bring this kind of active selection towards the sensor, we can make more efficient algorithms or efficient hardware. Like having a bit more smartness near the sensor might be quite beneficial for robotics.
Right, a bit more like high-level decision making. That's what you're saying. Yeah, and also there is another interesting thing that most of the sensors, the direction of data is in just one way. It's from sensor to the kind of like maybe downstream to the actuators or whatever is there. There are applications.
Yeah. Sorry, did you call my name? Sorry, my Zoom crashed.
Oh, welcome back.
Yeah, that's good. Yeah, so there are maybe, so this is the third topic that we're talking about, Ontario. And yeah, so some of the applications, maybe we just need to send data to the sensor. Maybe. I mean, we talked about this a while ago about doing like on-chip localization, doing some sort of rendering, sending image to the chip and doing some process on there. But at the moment, at least on a SCAM, we cannot do that easily. I mean, the recent paper that Hector's work is kind of like moving in that direction. But I wonder this would be something that we will need in future.
There's a whole reliability issue as well that one of the submitted papers was trying to talk about, in terms of if we have these on and near sensor processing systems, can we ensure that they're also, you know, doing accounting for bit flip errors or, you know, interference and all those sort of things. And if doing it on the near the sensor actually is a benefit rather than doing it on a larger CPU or something and trying to fix those errors there.
Coming back to the question, perhaps to me, one of the big opportunities here of these sensors is that we can open again the discussion about how to best process visual signals. So how to better understand the visual processing pipeline is something that so far we've been extremely not advanced and not very challenging, and challenge ourselves because we assume that these components exist, and to Boris' point, people prefer generality, and there are of course big gains on that. But as we move into applications, then you really need to start considering how best to do signal processing for specifically for vision. And I think so far we really don't have good frameworks for visual processing that are efficient. And this opens that discussion. This is part of that discussion that needs to happen. So to me, actually, that's a very good opportunity for us to revisit how to think about how to process visual signals. And sometimes one of the things that I struggle, it can be as basic as in our SCAM research, we don't capture images. We actually struggle to show our results because the SCAM is not designed to capture images. And this is counterintuitive to the notion of a camera that doesn't capture images. It cannot be a camera. But actually, this is what we need. We need visual sensors that work for the task at hand. And that task at hand may have nothing to do with recording images. So just rethinking what you're going to do with these visual signals is a very important discussion to have. And this I think, is a big opportunity for this type of sensors that we're discussing here.
Yeah, I mean, I agree with that. I mean, as you say, we're trying to figure out how to best process the images, but I think we're also trying to figure out how to best sense. So it's not necessarily that that the way of sensing, capturing frame is the best, and we see with event cameras work that actually, the different way of sensing is advantageous in some situations. We've done some work with Julian Martel, where he's capturing every pixel with a different integration time, and that allows you to reconstruct both high speed images and also high dynamic range images. So we have this all flexibility that people are just dismissing because we normally deal with these images that are captured in a very orderly way. So I think is the optimization of the entire pipeline from light to action that you know we have an opportunity to do with being able to process very near the sensor, because we can affect not just how, you know, what we do with the information that we capture, but actually how we capture that information in the first place.
Absolutely.
Yeah, exactly. I also think like it's kind of like we have to think about end to end, like from photon to action. That's how I think eventually it should be.
Yeah, that's right. And maybe if, I mean, I think another aspect of this is that having this ability to process things very fast, perhaps at a very high frame rates, or processing, you know, during light acquisition and so on, just allows you to rethink the algorithms themselves, right? It's not just a way of efficiently implementing the algorithms that already are there, but pointing to the new ways of solving problems that you would not think of applying, because there would be a completely non-economical in the conventional vision pipeline. Mm-hmm. So, I mean, doing things like we've done, for example, with the depth from focus, it really doesn't make a lot of sense to capture 7,000 images just to get the depth information. And yet it's not that expensive if your processing occurs as you're capturing those images without ever transmitting them out. So that sort of things where the thinking about the algorithms is really affected by the way that the compute substrate is organized. I mean, another simple thing is, you know, if you capture key points and you have several key points, if you do this really fast at, you know, tens of thousands of frames per second, then those key points never really move a lot, right, from frame to frame. You don't have to do key point matching. The matching is just by local proximity. So it simplifies a lot of things. So doing things fast, you can be pretty stupid and appear smart, right, just because you're quick. So I think that's quite interesting. So we really see the kind of different algorithms can be developed because of a different compute substrate that exists.
Right. Yeah. Exactly. A global sum is also another good example. I mean, on regular images, no one does global sum because it just doesn't make sense. But it shows its advantage with, although it's a very simple operation, but it shows its advantage on applications on SCAMP or similar sensors.
Yes. I mean, another example was in Boris's talk, this very nice kind of log gradients by division. It's really driven by the fact that it's easy to build a circuit that will do that kind of division, right? So it kind of that's how the circuitry drives the algorithm and not the other way around. And you know, it may well turn out that that's the way to capture images, and that gives you some other advantages somewhere else. So I think that really opens up the opportunities. And we've been sometimes, when we are discussing this thing, sometimes thinking something like a SCAMP, not the ultimate solution, but a vehicle for exploring the space of solutions.
Yeah, great. Sounds great. So, I think it's time to move to the fourth topic, which is about interfacing from sensors to actuators. We have seen a few nice works, emerging new works that are moving in that direction. But in general, like, is there new needs? Do we need to develop standards or protocols for signaling and things like that?
So what are you trying to get at here, Sajad, with what aspect? So with regard to like speed, or what would be different?
Right. So now, for example, if we want to send signal to to a servo motor. So we have to send some information to the microcontroller, and then the microcontroller sends the PWM signals to the servo motor. We might as well just output like PWM signals directly from camera. I'm not sure. I'm just thinking out loud. It's not maybe well equipped to do these sort of things, but we might as well rethink the interfacing and how the data is being passed down to actuators in terms of like, yeah, how they should look like. Yeah.
I think there's a lot of interesting stuff in that area in terms of like Riku said earlier, telling the sensor what to look at.
Right.
And you can do all sorts of sort of stabilization, image stabilization, and all that sort of stuff really quickly, and with the really low latency that you need for high frequency vibrations and things. If we can have yeah, actuators that are controlled directly from the focal plane. I do wonder if that is always going to end up being a custom design, though. If it's possible to have a standard there, or are you always going to have to co-design your actuators with your sense processing?
Yeah, or are there certain standards that would be so kind of generally important? I mean, like a kind of, you know, pan tilt capability of what a camera is mounted in, I guess, like an eye moving around, or like Waltera's wearable robot from the old days that just, and yeah, you think of Professor Ishikawa's, you know, just so many demos of how if you can track something at fixation, tracking just becomes so much easier. I don't think I'd seen that table tennis ball one before that. That's incredible. I didn't know they'd managed to do that. But yeah, you can imagine that you've got this intelligent eye, and then having that mounted on a pan tilt unit just may be such a common thing you might want to do that could almost be co-designed as a standard feature. They kind of interface to a pan tilt unit, and it's almost like this optokinetic reflex, or whatever, the vestibulo-ocular reflex, and these kind of things that a human eye has.
Do you have to do that physically?
Pardon, Paul?
Do you have to do that physically?
It's more efficient, Paul. Otherwise, you actually have a lot of high resolution. There is. Well, we can talk about that, but there is like a calculation of, if you actually wanted high resolution everywhere around your visual field, you will need an eye the size of 2 meters or something like that. So
sure. I think we might have talked about this before. I mean,
yes,
it's not so uncommon these days to see a 100 megapixel sensor. We don't want to be doing low-level image processing on 100 megapixels every frame, but we might use a perhaps separate sensor to select which.
To your point, even if you have 100 megapixels, but you actually have processing there, you might decide what you're deploying where, which will be still okay. So I think there is a path. I don't think we should discard any ideas at this stage, especially when we're trying to redefine the visual pipeline.
In terms of the interfaces with the actuation, Paul's mention of doing it digitally made me think: could we actuate the eye, the camera motion, pan tilt or whatever, with analog signals? Could we, bring it closer with I mean, we already in SCAMP, we already have sort of, negative charge, positive charge analog signals. Could we convert that directly into something that moves an actuator based on the charge?
I think you probably could, but then I think there's very limited, none I can think of applications that that actually call for that sort of, you know, closing the loop at that speed. I think we're talking about a single or a few actuators, and it's not a lot that you need to do along the line. So I don't see bottlenecks there in terms of actuation, unless there's some really extremely fast closed loop system. But I can't think of any that you couldn't do with a microcontroller.
I mean, I guess how fast is biology in moving your eye from the input, and are we matching that, or have we got ways to go before we're as fast?
The eye actually has a closed loop frequency of about 1 hertz, which is very fast. And you think 1 hertz is this, you can track that. But it's not overly fast. It's not overly fast, at least humans. I mean, bees and other flying insects have a much faster reaction time, which of course is very important to them. And so, yeah, again, there will be a range of requirements in terms of how fast you have to move. I will be worried if we just want to process things fast because we can. I think that will be the same as saying, let's just put more pixels because we can. I think, again, this opportunity that we have in front of us is how you can rethink what the visual pipeline actually requires. But going back to your point, Edward, about analog processors, I agree, and we have discussed with Peter a lot of times. We will love that the processors that are in SCAM, for example, are all analog and powerful and suffer from no noise or any degradation, because that is potentially a much better organic signal, let's say, towards connecting it to actuators. So, yeah, I'm just still waiting for Peter to develop that perfect analog processor that we can use.
It's not going to happen.
Oh.
So one of the ironies about that chain of reasoning is that we know biological vision systems are not clocked synchronous binary circuits. How is it that, why is it that we can't somehow retrieve or overcome the noisiness? I think this leads you to some kind of spiking structure, I think. I think I may have dug myself into a hole of ignorance already, so I should shut up.
I don't know the answer, I think, but I would love to understand better what is needed in order to improve analog processing.
I think Boris has hinted at the property of neural nets, which is that you're doing some sort of analog compute, and then you have a nonlinear operation, and that nonlinearity restores in some way the state of the system, right? So you can't have a very long chain of analog operations. I think you always lose something in the noise. But as long as you have this, nonlinearities in between that somehow, don't require you anymore to have the kind of linear or kind of remove the accumulation of the error, because they do some sort of decision, right? So it's always being selective in terms of maybe spatial and temporal selectivity, and then being selective in terms of making a decision and making some kind of, and that then feeds into the next layer, and that's that's how neural networks artificial ones work. Perhaps that's how the networks in the brain work. We don't actually know, right?
Right. Yeah.
Well, that's essentially an argument that with the right neural architectures, we can make the problem go away.
Oh, with the right architecture in general, right?
I think somewhere in.
I think analog computing. I think analog computing is it's efficient, but exactly it's not a solution to everything. It has to be interspersed with this kind of this digital or nonlinear stage where you can restore, and then you can keep going on for a long time doing this.
Right.
I think somewhere in there, there's the need to have a training process or learning process either on the chip itself or having a better simulator that we can use for training offline, so that we can actually, so things can learn the noise patterns properly, rather than these sort of approximations to noise that we're able to give them at the moment.
If you want to learn, I mean, if indeed the way that you want to build your system is through learning, but you know, it may not be the most practical approach to learn everything, you know, within the hardware that is operating.
Everything's learned, even if you're making up the algorithms by hand.
Yeah, good discussion. Let's move to the. We don't have much time, so and I understand it's Friday and evening for you guys. So let's finish up the discussion by the last topic, and it's kind of like interesting and challenging topic, especially when we talk about near sensor processing, SCAN5 particularly. So the question is, do we need better evaluation and benchmarking methods with focal plane sensor processors? Especially like you're doing processing right when you capture data. So if you want to reproduce data or someone wants to reproduce that, basically it's going to be challenging because the scene is not there. It's no longer there. You're not able to capture the scene. If you want to capture the scene, you're not going to be able to process at that speed that you want to do. So this is always a challenging problem. And maybe we should look for better metrics, such as like figure of merits that we use for ADCs or similar metrics. I'm not sure what's your opinion about this.
What does figure of merit mean?
I think Peter probably knows that better. Maybe if I define it, probably I'm going to make a mistake. But that's something they combine multiple terms together to kind of like give a ballpark number. Yes.
So you have multiple objectives and you kind of weight them all and add them all up. Is that what it means?
Correct me, Peter. I think you're the best person to answer this.
Yeah, I mean, I think, okay. I mean, yeah. Figure of merit would be something that captures the performance and kind of multiple parameters of performance and into a single number. I think, given that even a single, we cannot really agree what a single number means, like giga operations per second, and we know it's difficult to define that. I think defining even more complex figures of merit is a minefield. I think it's hard. I think in this field, because you know every sensor processor is different. Everyone works in slightly different principles, and it's really extremely hard to compare. I mean, how you compare an optic flow computed with events on sparse event data with an optic flow computed, you know, on frames. If you have two sparse flows which are at different points, essentially. I mean, at different points in time and at different points in space. So you can try to adapt the kind of common metrics to fit that, but it never kind of genuinely compares to different approaches. I think that's really hard. I think the best benchmarks are kind of task-oriented benchmarks. If you have in this field, so if you had a task and if you say, you know, I can track that ping pong ball with you know, with a particular speed and acceleration, you know, that tells you what the whole system can do. And I think that is kind of the fairest benchmark. But of course, these are also very difficult to set up. So I don't know what the answer is, but it's very hard to understand often, you know, what the system is capable of just looking at the tables of numbers that people publish. It would be nice to be able to do it straight away, but it's essentially impossible. Yeah.
Right. Maybe investing more on the simulation would be maybe reasonable. Just I mean, that's also kind of like doing good simulations is very hard as well, but I'm not sure doing like high fidelity simulations would make sense.
Yeah, it's not what would excite me. I'd rather just work on the real systems and try and make demos. I think.
I think there is an issue with, you know, just making demos and trying to make a science argument about what's working and what's not. I appreciate.
Yeah, but very often we're kidding ourselves, I think, with these metrics. I'm just sick to the back teeth of papers full of tables at the moment in this field. You know, the world is wide open. We've got, you know, orders of magnitude of improvement to be needed, and we're already defining benchmarks in far too many places. It's my little rant at the moment.
I think I echo that. I think the challenge for us, Andy, is, however, what are those demos that are going to be groundbreaking and that are going to say, yes, I don't need metrics because you're showing me this, right?
Yeah.
I think that will be the challenge.
No, sure. I mean, that's always the challenge, isn't it? Yeah. But yeah.
Yeah.
I guess we've done it before. We've done it before. We're trying to do it again.
Yeah, let's do it again.
I think part of the subtext for Sajad's question, in my mind at least, is that within a sufficiently constrained and conventional environment, you can see how to make, you know, benchmarks, and we've done it with things like SlamBench, and such things are much more common in other parts of computer science. What we might imagine trying to do is to do this in a way which doesn't constrain the design of the solution. And at that point, you start confronting things like, you know, if you wanted to study, do reproducible experiments on the per pixel exposure control, you know, you can imagine a simulator that would do this, but it's not what you wanted. What you're actually looking for is something more like an agreed experimental protocol.
Yes, yeah, exactly. That could basically, yeah, that could kind of like put us in that direction. Maybe we need, say, for example, repeat one experiment 50 times and report the average, for example. I mean, things like that. If it's not really possible to reproduce exact same experiment. And I totally agree with Andy that, like, if the demo works, that's pretty good, and that's going to work only for the first paper. And Andy has a lot of papers like this, that the first paper in the field, and so it's everyone accepts it. But if someone comes and wants to compete, they're going to refer to the previous paper, and they're going to ask, like,
there's also a tension here between innovation and technological engineering.
Right.
So ideally, we have academics, like some of the people around the table, making shiny new things, turning them into engineering products, and making good engineering decisions about A versus B. Actually does involve doing repeatable experiments. They don't have to be public benchmarks. They actually need to be things of business value.
Right. Yeah, and this is still a challenging for SCAMP. So I think we need to come up with a protocol or something like that. And now, for example, just for SCAMP, we have 4 different techniques of doing convolution. We have OK framework, we have Kane, and we have 2 papers that Laurie authored them. So we have 4 methods of doing, at least the 4 methods that I know. But comparing them is quite difficult. So if a 5th paper comes along, so we have to be able to kind of like say what are the pros or cons. And this is more challenging with this camp.
Yeah.
I guess if it's just a composite, maybe the semi-simulated environment, which was proposed in the poster, would be quite nice because we can load a known image and just apply the convolutions on the scan. Again, it's probably not the same as having a moving camera and trying to capture something.
Right. Yeah, exactly.
It seems like the golden standard would have to be a robot arm that everyone can get, and you can put whatever camera you like on the end of it and have it shake around in a particularly drawn out scene that's very well specified. I mean, but the idea is that, you know, you're making your benchmark task based and like real world rather than simulated, rather than yeah. So you can allow for different cameras, you can allow for different processing examples, but what you're actually constraining is the specific task, the movement of the camera for, you know, localization or something, and the scene itself.
Yeah. And that's only for one application. If you change the application, say for example, maybe driving in a crowded like streets, or yeah, it's going to be very hard to repeat that.
Yeah.
Yeah, I think that would be one of the challenging problems, and we need to come up with a solution.
I think there's an interesting benchmark that seems to be implicitly seen so far, I think, throughout this day, which has been the can you reconstruct the original image benchmark.
Mm-hmm.
And if that plays into how we benchmark or decide how to evaluate different techniques for doing this on focal plane sensor stuff.
I guess the main purpose of trying to do more computation near the chip is that we cannot construct the image back because we've already handpicked or selected the most important information, such that there's basically nothing to squeeze out anymore. And I guess if we make the benchmark to be that, can we make a image back? People would be, I mean, the best one would be to just send all the images. So
yeah,
I don't think.
More broadly, the question is, can you actually complete the task with just the data coming out? Could you, can you give that data to a person and ask them, right, from that data, has it told you what you need to know? Obviously, you're sort of defaulting back then to making a pretty picture that humans can see. But there's yeah, I guess it's task dependent, isn't it? There's no one single solution.
Well, I guess another way to benchmark would be to just make the tasks harder. For example, we might imagine like a tracking task, which is can we track 100 kilometer ball or kilometer per hour ball? The next one would be 200 kilometer per hour. And then we solve the problem of, well, we sort of solve the problem of not having to benchmark, and the next paper to be good enough to be able to solve a harder problem. And I think that's enough to justify why the successive papers are good.
Exactly, 0 to 1 demos. Do something for the first time. That's what, yeah, that's what I like to try and do.
Mm-hmm.
Great. So I think we're 10 minutes over the scheduled time. I think I really enjoyed the discussion, but if there's nothing left, so we can finish this here.